Dr. Lisa, can you hear us?
Yes, I can hear you
Okay, hello,
clearly.
good
Hello.
morning.
Morning. It's
Hello.
Abdullah, is it?
Yes, I
Yeah.
am.
Ada Tabla, how are you? Sebab
I'm
Kak Cham
fine.
pakai mask.
Yeah. Yes, I'm wearing mask now.
Okay,
Okay.
okay.
Thank you, Dr. Lisa. You can start now for your topic about stellar modeling. Okay, please.
Okay. All right.
Until 9:30, and then we have break, and then we continue after 15
Okay,
minutes. Okay,
thank you,
please.
Dr. Rila. So, good morning, everyone. So, I hope that you can hear me clearly today. Okay. So I guess that I think half of the participant is coming from the ITB itself, and probably you have learned about stellar physics thoroughly from your lecturer, right? So, but here I'm going to, since the organizer mentioned to me that I have to prepare this one for the undergraduate level, so I try my best to what they call it, give a lecture, which is kind of general, but with the sense that how we implement numerical modeling when we want to build a stellar models. Okay, so good morning, everyone. My name is Norhasliza Yusof. I am from University of Malaya, Department of Physics, Malaysia. So I'm pleased to be here to be with all of you to give this lecture this morning. Okay, so I shall start now giving a bit about the what is stellar structure and evolution. I'll give some brief, what we call it, history, or the what we need to know when we want to build a stellar structure and evolution models. So when we speak about stellar structure, one thing that come in mind is we are only focusing on the stellar interior, which we do not consider the stellar atmosphere, as you can see that in the structure of the sun here in this what they call figure here. Okay, so we consider only from the center up to photosphere level, and photosphere and upper is the what we call as a stellar atmosphere. So when we want to build a stellar structure, we purely consider the interior itself, or what we call as a stellar core. Okay, so in order for us to build a stellar structure models, we need what we call as a nuclear energy and pressure to support the stellar structure, which is considered the most important, what they call it, characteristic or properties in the inner region of a star. And one thing, although now people speak about 2D modeling, 3D modeling, and so on, the stellar structure and evolution currently still in a 1D, right? So we solve it in 1D because it's a numerically rigorous, what they call it, task. So we simplify everything into a 1D, and we consider our star looking only in a one-dimensional perspective. Right. So if we know that in the property of the star, at the center and the surface, this is for example the center we learn from the standard physics, what they call it, knowledge, and for the surface we learn from the observation and so on. And these two parameter is known as boundary values. Okay, and in order for us to solve stellar structure equation, we need to solve it in order for us to obtain the value between this the surface and the center. So from each numerical calculation, what, for example, the radius or mass will move with certain coordinates. So this is the characteristic that we have to, or the properties that we have to know in order for us to understand what is the inner core in our stellar interior. Okay, and when we speak about to solve this kind of numerical problem, and it requires a special numerical technique, we will learn that in the second half of our lecture today. Okay, all right. So when we speak about stellar structure, we have structure. Okay, so we have what they call a sphere of star, and then we speak about evolution. Okay, so there are two parts when we want to solve in the modeling. So first we have to build the structure, and then we have to evolve with time. Okay, so this means that a stellar evolution evolved from time zero. Although now we can also evolve from a pre-mean sequence, which is the negative of time. But here we consider first at time zero. This is also we know as a zero-ish mean sequence, where the hydrogen start to burn at the core of the star. and we can evolve it until what we call as a pre-supernova stage, or at any desired age. Okay, desired age, for example, if you want to know the age of the star of a sun, for example, we can start our evolution at that particular time. So if you don't want to stop at, for example, at the age of star, we want to see either it evolve into a white dwarf or whatever, we can let the evolution to evolve until what is our desired what they call time. Okay, so the time here we speak is in terms of billions of years, million or billion of years, depending on what type of stars that we want to study. Okay, so if you want to have a smaller star, we might have what they call it longer lifetime, and if you have a bigger star, because the lifetime is shorter, so the lifetime become only a million of years. Okay, so when we speak about the evolution that move with time, it requires to solve a nuclear network throughout the time. So this is where the rate of time come in the stellar modeling. Okay. So when we speak about what they call it a stellar modeling, in perspective of an astronomer, we always know that we have what we call as a HI diagram. Okay, so the one that I've shown here. So when we speak about HI diagram, the only things that observer or astronomer interested is we want to know how bright is the star, and from the brightness we can deduce what is the temperature. For example, what is at certain temperature, either our star is at the cooler or the hotter region, and what is the luminosity of our star, or the brightness. Okay, so this is the one that people observe. So all the point here is only one, for example, particular, for example, sun. I think example of the sun. So at that point, we know what is the luminosity of the sun and what is the temperature at that particular age. Okay, so but when we want to calculate the stellar models, we have to calculate from time zero. So that's why you can see on your right hand side, the one, this is coming from the stellar models. Okay, so from here we calculate from ZAM models. Okay, so this is one of my work, and then we can map for with the observation. For example, what people observe, this is for the massive star, the one that I've shown you from the calculation. Okay, so when we know that what is the mass of, or what they call it, the luminosity or temperature at the observed stars, we can calculate or estimate the stellar evolution model from ZAM until it evolved, and then we try to match it to see that either where is the observed object can be located in our diagram. Okay, so this is how people estimate, for example, the mass, or what is what they call it, is it the exact luminosity or temperature for that particular observed object. Okay. And another thing, this is in terms of evolution. I don't go to the structure yet. Okay, so from here, another things that when we speak about evolution, we want to see what is the change of the temperature density relationship. Okay, so for example here, we want to see that when we want to observe some temperature density relationship, how does the, for example, the process, the what they call the change of a gaseous process or plasma process occur when we have different mass evolving, and then what are the particular temperature of density that needed for that particular star. Okay, so one thing that we did is we know that we have observed a lot of stars. We know the property, the abundance, luminosity, and temperature, but usually we don't know what is the age. We don't know what is the mass. Okay, so by using this evolution, we can estimate at what particular what they call it age of our star evolve. Okay, so this is another temperature density. This is a grade of models, mean that we calculate from a very small mass 0.8 up to 300 solar mass, and we see that how the rate of temperature density, which is govern our star, evolve with time. Okay, so we can see that as we go for the higher masses, we have extremely very hot and very dense star, right, compared to the lighter one. Okay, so now we move on to the what they call it, the assumption on how we want to build a stellar models. Okay, so to build a stellar models, we make some assumption. This is what people, especially when you study physics, will do before you want to build something, or you want to solve something. we have to make several assumptions to simplify our calculation. Okay, so first of all, we assume that our star is spherically symmetric. Okay, so whatever the what you call the plasma or the gas moving in our star, it will be purely in a sphere and is symmetric. Although that people observe that the star might not be spherically symmetric, but this is for us easy to compute the models. Okay. Another one is the star is in hydrostatic equilibrium. What does it mean? It means that the internal pressure, which is equivalent to gravity contraction. So means that if it is not hydrostatic equilibrium, the star will be easily what they call collapse. Okay, so this is we want to prevent it to collapse in a very early age. So we assume that it is in hydrostatic equilibrium. And another thing is the energy must come from the nuclear network. It can be either a proton-proton change or in a carbon nitrogen oxygen cycle. Okay, depending on what is the mass that we want to estimate, the nuclear network will change eventually. For example, if you want to calculate for suns, like a very small star, the main nuclear network will come from the proton-proton change. But if you want to calculate for massive star, for example, the main energy coming from the CNO cycles. Okay, so this is due to the temperature density of the star is different from one mass to another mass. Okay, so we have to identify what is the star or the models that we want to calculate. And then we have a uniform initial composition at start. Okay, so when we want to start to model a star, we have to put our composition, our hydrogen, helium, metal abundance, and so on, as a what they call it, as a certain uniform composition. So after that, it will evolve with time, and then it will have the change afterwards. Okay, so the change will coming from the time. All right, so I move on to stellar structure equation. Okay, so when we speak about stellar structure equation, okay, stellar structure equation is being governed by 4 differential equation. Okay, so from here you can see that we have 4a and 4b, but don't worry about that, because why it will have 4a and 4b, because this is due to the what are the transport mechanism be implemented for that particular star. Okay, so first of all, when we speak about hydrostatic equilibrium, and then we assume that our star is in the spherical symmetry, you can see that the rate change of mass with radius is equivalent to 4 pi r square rho dr. So this is coming from the assumption of our star and also the pressure and gravity. Sorry, this is from the what they call it. I think I mix up this one. This one is actually for the mass conservation. So the first one. So the first one is the mass conservation. So we have to do the hydrostatic equilibrium, and after that we have the dm over dr is for the mass conservation. Sorry, yeah. So this is I have to create, and then for hydrostatic equilibrium is for the pressure with the rate of radius. Okay. So from here, this is where we have the what I call internal pressure and gravity, and this is for our mass. I will correct this slide afterward. Okay, and after that we have energy equation. Okay, so the energy equation, you can see that the output is actually the rate of change of luminosity or brightness with radius. Okay, so when we have this kind of energy equation, we can see that we have this epsilon here coming from the energy. The energy can be either nuclear energy or neutrino energy, depending again what is the mass of your star. And then we find the difference of the temperature with the change of entropy. Okay, so the S over dt is the entropy of that particular star. Okay, so when we speak about star, definitely we have a temperature difference. Okay, so temperature difference can be two ways. Either we have what we call as a radiative transport. Okay, when it transports or the additive convection. Okay, so for example, if the star is purely radiative, like our sun, for example, we have to use equation 4a. And if we have more massive star, right? So the star that with, for example, 7 or 8 stellar mass. So the radiative transport will change into what we call as a adiabatic convection. Okay, so some stars they have both of them, but it will change when we have what they call it, when the pressure or the what they call it, the gases is changed rapidly throughout the evolution. It can change, and this is will follow either, for example, a Schwarzschild criterion, for example, right? So this is one thing that we have to consider when we want to calculate the stellar structure. So when you see that all the stellar structure is actually in the differential equation, okay? So dm over dr, dp, the pressure, rate of pressure, the luminosity, what they call temperature, and so on. All these are in differential equation, meaning that everything we treated as a 1D. But eventually, the original structure equation is in a partial differential. Partial means that del m over del r and so on. But for the sake of modeling, we transform everything in terms of only the differential equation. So that we only consider one variable at one time, which is actually our radius. Okay. Right. So I just give some what does it mean by all those what they call it variable and parameter that we use in the stellar structure equation. First is the mass. What is in the bracket means that the mass will depends on the radius. P is your pressure. L is the luminosity or the brightness. T is temperature. So the temperature, when we calculate the stellar evolution, we have two temperature. One is the center and one is the surface. Usually the center we call as a TC, central temperature, and in the surface we call as effective temperature. Okay, it will depends on how we define later on. And then we have density rho. Epsilon is our total energy. This is a nuclear plus neutrino. Okay, so first of all, the energy must be what they call governed by the nuclear energy first. Okay, so neutrino will come later on due to the what they call it the option, either it produce it or not. Okay, and it is depend on the element abundance. So like myself, I did a lot of massive star. I have to consider both nuclear and neutrino, because if you don't have neutrino in our star, the star cannot cool. If there's no neutrino, the star will be heated very fast, and then it will explode quite early. So the neutrino will keep the star cool, what we call as neutrino cooling. So it will emit neutrino when the star start to evolve, especially when it start at the carbon burning or at the carbon station. So from there it will emit so that the nuclear and neutrino energy will balance out the structure or the structure of the star itself. And then we have entropy. Entropy is coming from the thermodynamic equilibrium. Thermodynamic what they call it that govern the star. And then we have time. Time is where the star evolve. K is this is kappa, opacity. That is, we have to know what is how opaque is our star. This is for the what they call it energy transport. And then since our star is actually the ball of plasma gases or plasma, because it's ionized, and then we have what we call as a adiabatic index. Okay, so this is related to the pressure and temperature because without this the star cannot survive. And then a certain variable, for example, A and C here coming from the radiative, A and C here coming from the radiative transport is actually just a constant from the Stefan boson constant, because this is coming from the what they call it radiative transport. And then we have gravity constant for the hydrostatic equilibrium and also speed of light. Okay, so this is all are the parameters that require when we want to calculate the stellar structure equation. Okay, so the next question is either we want to calculate in terms of Euler or Lagrangian. Okay, so this is one thing that when we want to solve for stellar evolution, we have to consider these two things. The original equation here, 1 until 4b, is what we call as in the Euler coordinate. Okay, so this is all. Another word is a Cartesian coordinate, because it's moved with the radius of the star. Okay, it will move from one value from the center to the surface according to the radius. Okay, And this is what we call as R as an independent variable. So we change R. So others, what they call it variable, we change according to the R. Okay, so another option is what we call as a Lagrangian coordinate, where the coordinate will move with the motion of the mass. So instead of use R, we use mass. Okay, and then now instead of radius, we choose mass. So why? Okay, so why we want to transform equation 1 until 4.b into a Lagrangian coordinate? We don't want to use Euler. Okay, so there are a reason behind this. Okay, so one thing is we have abundance. Abundance is not yet coming in 1 until 4b. So the equation is not that here, is coming from the epsilon. So the epsilon do have their own calculation for that. Okay, so the abundance, or what we call as chemical composition, are actually in a per unit mass. Okay, so when the abundance is coming from what we call as a fraction of unit mass, and this must be calculated in terms of mass coordinate. So what happened now, equation 1 until 4b, we are going to transform it into a mass coordinate instead of radius. So now mass will become our independent variable. Okay, so now our solution from our stellar structure equation now written in terms of the radius depend on R, pressure in terms of radius in terms of mass, pressure in terms of mass, temperature in terms of mass, and luminosity in terms of mass. So every output now is actually will change with mass. Okay, so the advantage by using this mass instead of radius, because when a star always have, because due to the hydrostatic equilibrium, it always expand and contract. Okay, so here when it's expand and contract, the composition will remain constant due to the mass, and if move with the gas. Okay, so if we use the radius, what happened, it will have some difficulty that at particular mass, we don't want the abundance to change rapidly. Okay, so this is also due to the stability when we want to calculate a stellar evolution. All right. So now equation 1 until 4b, we can transform into as a mass independent variable. Okay. Now here we have the rate of change of radius of m, the energy, the luminosity, pressure, and also both for the radiative and the convection. Okay, so you can see that here, what happened now, if you see compare with the one that we calculate with the Euler coordinate and also the mass coordinate, you can see here in a in the radius coordinate, all equations do have density. Okay, so 1, 2, 3, 4, everything do have a density except for the adiabatic convection. But now you can see that when we transform into mass, only for the radius contain the density. You can see that in other equation, the density is vanished. So meaning that because density also change when we change the mass or radius, so it means that this will be simplify our calculation and going to optimize our numerical work, because the density will only change when we calculate the rate of radius. Okay, so the density must remain as what we call it important parameter or properties in the star, because we don't want it to, because if you calculate it wrongly, it will affect all the what we call it equation. Because why? When we want to calculate stellar evolution, all these 4 equations will move simultaneously. We don't solve it one by one. We have to solve it in one go. So each time we calculate the stellar evolution models, it will eventually calculate everything at the same time, simultaneously. That is what does it mean by simultaneously. Yeah? Okay, so here now we have our solution that I mentioned just now. This is the output that we obtain when we calculate the stellar structure equation. Okay, so this is where we can we see what is the radius of our star, the pressure, the temperature, and luminosity, and this is the properties that we are going to use, for example, when we want to compare with the observation, for example. because usually astronomer only cares about the surface. They don't really care about the interior. So, but eventually we have to calculate from the interior so that we can get the output at the surface. Okay. All right. So when we speak about stellar structure equation, another things that we need and our input, yeah. So or our what they call it, the phi structural variable at the local thermodynamic as stated as here. So we need again our pressure, even though in our equation we calculate the pressure also, but here we also have to initially put what is the pressure of for the particular star, especially at the boundary condition. Okay, so the pressure, opacity, energy, entropy, and also the adiabatic exponent now depend on three variables. Okay, so it depends on rho. You can see everything is depend on rho, temperature, and also the abundances, or what we call as composition. So it means that each time we want to calculate for this particular or we want to set this particular variable, it will move with all these three variables. It depends. So meaning that when we have these three variables, it means that it depends to this three variable what you call at one point. Okay, so if you don't have temperature, we only have a rho, or we don't have abundance, so the pressure we cannot calculate it. So that's why we need all these three variables in order to obtain all this what they call it, properties. Okay, so here later on I will explain to you what are these things. And then in order, you can see that we have pressure, opacity, energy, entropy, and adiabatic exponent. And this is what we call as the input physics. So if you read papers, or if you what they call it, try to learn stellar evolution code, the first thing it will ask you to do is what are the physics input for you to implement in the stellar evolution code. Okay, so one thing is that we have to give opacity. This is coming, for example, some opal table for the opacity composition. And then we have a nuclear reaction rate, which is coming from the what they call real clip, or from the what they call it, the compilation of this NACRE compilation, because we have the rate is a lot, so we have to compile all the reaction rate. And then we have neutrino loss. This is we take from analytical calculation. People have calculated for especially for the late stage evolution for the massive star, in order to keep the star cool. And another one is we have to set what we call as initial composition. Initial composition is, for example, we want to know, we want to calculate at what particular galaxy is the star located. Okay, so and then we have to know what is the abundance. The abundance, for example, the famous abundance, we have to use Asplund, Griffiths, and what they call it, Reef, and so on. We have a lot of initial composition depending on what are the best thing to fit the result. So we have to choose this one. So the composition, usually we say that hydrogen around 70%, helium is for example 20%, and others element is actually the difference between the hydrogen and helium composition in the star. So that is, and then we can evolve. So another thing that I don't mention in this slide is for example the wind, or what we call as the mass loss. Okay, this is important, especially if your star rotate. So here I don't mention about the rotation. So for example, if the star rotate when it's evolved, there is some contribution from the winds, okay, stellar winds. Okay, so stellar winds means that when the star rotate, there is the what they call the mass, which is your abundance, will be ejected to the what they call it throughout the atmosphere. So this is another thing that also as an input physics, but here I don't put much. But later on, when we want to study this mass celestial evolution, we can see that how we can change all these parameters and obtain the observable what they call it models. Okay. All right. So, and then I already always mentioned about the chemical composition. What are those? Okay. So chemical composition is also known as an element abundances. Okay. So when we have two aminoacids, this is also coming from the nuclear reaction, or if you read books or paper, this is also known as the nuclear burning. Okay, so because we have to burn our hydrogen initially at our core, and after that the hydrogen will change into other heavier element, and this process will undergo millions of years. Okay, so it depends on what are the type of star that you want to calculate. So the nuclear reaction network will play important roles to determine that either your star will die early or will stay longer. Okay, so this is why the evolution, so you can see that now the chemical composition, this is where the rate of change time come in place, right? So you can see that this is XX, means that we can change into hydrogen, helium, and so on. Okay, so this is the rate of composition, and you can see that it will change with the time in the Lagrangian coordinate. So that's why, since everything is Lagrangian coordinate, so we have to transform the early evolution equation, stellar structure equation, into the Lagrangian coordinate. Okay, so from here we have the atomic number, the mass of our what they call it, chemical composition itself, divided by the density, because it depends purely in density and temperature also. But here we don't have the temperature. Temperature will come in the what they call it, in another equation. And this is just the summation of how much nuclei will change, multiply with the reaction rate that we at that particular time. Okay, so when we see that, for example, at the main sequence where the hydrogen burn rapidly, so from there, for example, we have all the what they call it, PP chain nuclear network will calculate with time. Okay, plus with the mixing. Mixing is either what kind of mixing that we want to do, because here it depends again what are the type of star that we want to calculate, right? So some star we don't consider mixing, and some we consider, right? Okay, so this is the what they call an overview of how the nuclear network looks like. Okay, so for example, for the sun, we have a proton-proton change. So that's why we see that it's come with time. So in order for proton-proton to fuse, it will take around 10 power 10 years. Okay, so it's a very long time. Okay, so at this point, our star, or for example, our sun, still burning what they call it, hydrogen. PP is a hydrogen, proton-proton is a hydrogen. It's still burning proton-proton or hydrogen, and it 10 power 10 years. This is very long time. Okay, so from here, in order for hydrogen to produce another element, okay, so for example, this is a neutron, proton, neutron, and it produce positron and also neutrino. It will have to have a very long, what we call it, a lifetime, and this one, it will produce what we call as a change of reaction. Okay, so eventually hydrogen will fuse, and then what they call it, the product that it produce will again fuse together, and in the end it will depends on what branch that we are going to calculate to see, depend on the time. It will produce helium-3, helium-4, barium-7, lithium-7, all boron. So this is all the change of reaction that produce heavy element. When the temperature and density change, the proton-proton change will eventually change to a CNO cycle. Okay, so this that's why it is important for us to evolve. This is the keyword for the stellar structure evolution, in order it evolve with time. If we don't put nuclear energy in our stellar structure, we only get a structure, not evolution. Okay, so this is the things that we have to bear in mind. All right. So I think I make the lecture a bit fast today. Any questions so far? Before I move to more, what we call it, technical things. Everyone want to ask anything?
Still any question?
No? Yes?
I think no. Everyone in the Zoom? Still any question?
Hopefully they are not sleeping when it's still morning.
Or in the
Okay.
class? Okay. Maybe you can continue.
Okay. So right.
And then we will ask question again. Okay.
Okay. Okay. No problem.
Okay.
Okay. So now we are moving into what we call as a boundary condition, right? So since I assume that all of you have listened to the numerical what they call lecture, I think in the last few days. Okay, so I hope that you can at least grab some what I call information on why we would need to study numerical technique in order for us to calculate boundary condition. Okay, so how we model a star. Okay, so in order for us to model a star, we have to set a given mass and composition, and then we have to compute with time. Okay, so from here we can see that we have what they call it. For example, we want to calculate for a sun. We set our mass of sun is 1 solar mass, and then we set what is the initial composition, and then we evolve from time 0 until 4.6 billion years, for example. Okay, so from there we can get the properties of our sun. Okay, so in order for us to solve the stellar structure equation, we need to integrate it, the set of structure, the one that in the Lagrangian coordinate, from the center to the surface, and then also from the surface to the center. Don't get confused, we have to do both, right? So you can see that why we have to do both way, why we don't just integrate it directly from what they call it center to the surface and then get the result. The reason is due to the stability. Okay, so the nature of the differential equation itself is not stable enough when we want to solve direct integration. Direct integration means that we integrate from 0 to r, for example. And then we also want to avoid our solution become infinity, especially we have 1 over rho. Okay, so if the rho becomes 0, what happened is our equation will become infinity. And what happened that, and then our code will crash. So we don't want to do that. Okay, so here in order for us to avoid that, we have to do 2 ways. Okay, and then we find the difference later on. Oh, sorry. Okay, so when we speak about the boundary condition, okay, so the boundary condition for the differential equation is the important part when you want to solve the stellar structure and evolution. Okay, so what happened is not all boundary condition can be specific at the end of the interval. For example, at mass at 0 and what is at that particular mass. Okay, and then some of the boundary condition we set at the center, another one at the surface. So it means that we have two what we call it boundary condition. When we have two boundary condition, it means that we have to, oh, sorry. Okay, so we have to set two conditions, one at the surface and then another one at the what they call center. So what does it mean? It means that when we want to integrate for a forward integration, it means that from 0 until whatever we want to constrain, and it's not possible. We cannot do that. Okay, and then why? Because this is the influence of the boundary condition. Solution is not easy to solve. Okay, so what happened now? We have to set what we call as a boundary condition at particular mass at 0. Okay, so this is at the center. We have to set the radius is 0 and luminosity is 0, because at the center there is no what we call it brightness or intensities. Okay, so we start the radius at 0 and L is 0, and then we can start at particular mass. This is at the center, and then we can start to integrate. Another one we have to set is at the surface. So we have to set the mass at particular m. So m can be anything. You can set, for example, at 1 or 10, whatever. And then T is actually the we set at the T of photosphere. pH means that surface of photosphere, temperature at the photosphere. And then the pressure also the pressure at the photosphere. Okay, so this is the boundary condition that we have to set both center and surface. So what does it mean? It means that the numerical method to calculate the stellar evolution is not an initial value problem. So what is the initial value problem? Initial value problem is where we only set one initial, what we call it, the value, and then we can solve the integration directly. But in this case, since we have to set what they call it, two boundaries, it becomes what we call as a boundary value problem. The boundary value problem that we have to set one point at the center and another point at the surface. This is what we call as a BVP, boundary value problem. And from there, we can see that how that we can solve these two boundary problems. We have to either to adjust or we have to find the difference, whatever. It depends on the technique that how we want to solve this stellar evolution. Okay, so here I just make a very crude, what we call it, diagram on the simple structure of the star. So, well, this is not according to the scale. I just do it very fast. So the red dot is where your, what we call it, the center is. This is where the M is 0, the radius is 0, and also the luminosity is 0. Okay, and then here it will move with radius or mass, for example, for the Lagrange coordinate. So this is the radius here for each, what they call it, a direction is the same. Okay, so because we consider it as a symmetrical symmetry. Okay, and also here we have up and down. It means that we have a pressure, gravitational contraction, and a pressure pulling inward and outward in order to maintain the stability of our star. So the photosphere is actually just the line here between the yellow and the blue one is where is the photosphere is located. So that is what we consider as the surface for the stellar evolution or stellar structure calculation. And the yellow one is your stellar interior. And the blue one here is what we call as a stellar atmosphere. Okay, so from here is the chromosphere and so on. So this is, we don't solve the blue one, we solve purely the, what we call it, the yellow one. And here you can see that this the center here where is the starting point before we want to solve everything. And at this particular boundary, the photosphere, the one or this value here is located exactly at this point. You can see later on the value of photosphere is what we call as optical depth. It's extremely what they call it, we consider is a thin value, it's a very small value, and it's adjustable depending on what type of star that we can calculate, we want to calculate. We can adjust it accordingly so that we can see that how it can solve eventually for a particular star that we want to calculate. All right, so now we move on to what we call as the central boundary condition. Okay, so at the center of the star where the mass is 0, okay, so what happened now, both our, what we call it, density energy must remain finite. Okay, so when it's remain finite, it means that both radius and the luminosity must vanish at center. Okay, so it means that at the center 0, R0 and C0. This is what I mentioned before. And here, but the center value for pressure and temperature is unknown. So that what happened now, this two boundary condition must be specified at the surface instead of the center. Okay, so now since this is unknown, this is 0. So at the surface, we have to put the value. So if not, if everything is unknown, we cannot solve it, all right? So here, in order for us to get the behavior or predict the value close to the center, we can use a Taylor expansion. Okay, so when we want to solve a Taylor expansion, it means that we expand our, what they call it, equation. We have to integrate first. Okay, so the one that we have here, for example, I go back to this equation. So for example, we have our project equation. We have to integrate our equation. And then we have to expand using the Taylor series or Taylor expansion, and then we get the approximate of the pressure at the center plus the mass and the rate of change of pressure with mass at the center. Usually Taylor expansion, you know that we have a very long expansion, but for the stellar evolution, we only take the first order. Okay, so for us to make it easier to calculate. So when we have the first order, what happened now is we can estimate what is the pressure at the center. And then here mass is already known. And then we can see that what is the rate of pressure when the mass is changed eventually. All right. So now we move on to the, what they call it, surface boundary condition. So when we have the surface, what they call it, condition where our mass is m, m means that the value that we set, and then the radius is r, where the radius will change because at the surface radius is 0, and then when we move with time, the radius is what they call, we have value, and then the boundary conditions are generally much more complicated than in the center. Why? Because we have to make sure that this value must be treated in correctly. Okay, so if you don't put the correct value at the surface, what happens that you might not get the one that we desire, or what are the value that we are, what they call it, looking for. Okay, so the simplest option is we have to take at temperature 0 and pressure 0 at the photosphere. You can see that now at the center we have a value for the pressure, but at the surface is 0. So this is what we call as a zero boundary condition. Okay, so but reality is the temperature and pressure never become 0 because the star is surrounded by the interstellar medium, and we have a very low but finite density and temperature. So it means that we have maybe it's around a few percent of temperature or pressure at this particular point. But here, because for the simplicity in for the stellar evolution calculation, we do it quite, what they call it, crudely, so that we can evolve the calculation without any crashing or so on. Okay. So I think I'm going to finish in another few minutes more. The next part will be the second part. Okay, so the surface boundary condition is what we call it, we have a better option is with the photosphere. Okay, so we know what is the photosphere value. So where we have some radiation, what they call it, move or escape, which corresponding with the visible surface of the star. So what happened now, we can estimate photospheric boundary condition with a single surface, what we call as optical depth, with tau is 2/3. Now what we can do is we can estimate the optical depth is just what they call it, integrate from the radius until infinity, because we just put some, what they call it, assume that until what are radius that we want to what we estimate with the kappa and density with respect of the radius. Since kappa is known, okay, so kappa is just a constant, so we only need to integrate for that particular density. Okay, so when we want to do this, this is mean that our calculation must be easier, and this is the second part in order for us to match our center and our surface condition. Okay, so here when we have the atmosphere is very thin, okay, so very thin, what happens is our stellar structure equation can be simplified just as our pressure, and then the gravitational and mass is we consider as a constant with R, and then we just again integrate with the density only. Okay, so because this is we already know at that particular surface, and from there we can estimate easily what is for the surface, what we call it, value for our pressure. Okay, so here our optical depth is around 2/3, which is quite small. And what happened now, our temperature at the surface, this is what we call as effective temperature, the one that people always deduce from the isochrone or from the observation, for example. From there, we can combine these two equations with the, and rewrite back the photospheric boundary condition as the mass. Okay, so mass at a particular radius equivalent to pressure, and we put that, and then we get the term of pressure. Since we have this term of pressure, we can solve it easily because we no longer have to solve it by using the efficient equation. Now we have a set of equation that we can estimate directly what is our pressure is. This is as our initial value, and also for the luminosity. Okay, so this is what usually people estimate in order for us to get at the particular surface, what they call it, value. All right, so I stop the lecture here before we move on to the second part after this. I think that I give lecture quite fast today. Any questions so far?
Okay, thank you, Dr. Lisa. Any questions from the audience? From the other participants? Okay. We have here in the chat
Yeah, okay.
from Sophia. How do we get to that for the value of optical depth? Maybe you can answer.
Okay, so from here, sorry, I hope the voice is not echoing. Okay, so from here we get the what they call the depth is coming from the estimate of the photosphere. So here there is some, I think the equation to calculate the optical depth, if I'm not mistaken. So it depends on different, what we call it, different type of star. There is a certain value for that particular optical depth. Okay, so for example, if you see that for massive star, the optical depth is around 0.1, 1/10. Okay, so maybe for those who are doing the atmosphere can answer better than me, but here we just put some estimate in order for us to get the optical depth. Because here the optical depth is can be changed due to the we want to integrate for the center and the surface for that particular value. Well, I might not really answer the question, but that is what I know in order for us to calculate the optical depth.
Okay.
Anything else?
Okay, is there any from the class? No. Okay. Maybe I have a question for you, Dr. Lisa.
All right. I think you are yourself. You're doing this time.
Yeah, I'm in about. I think I will ask about the mass. If we have different masses for the stars, what kind of effect for the for the equations that involve in the stellar evolution?
You mean this equation?
Yeah, you can say that. If we have different mass, we have from the small one, maybe from the one solar until maybe 60 or 40 solar mass, maybe. Is there any different?
So the difference will be what we call it, how we estimate. Okay, so one thing that I discovered when doing smaller and also more massive star. So for example, for sun, right? So for sun, we can easily determine what is the, what we call it, the properties of our temperature at the condition, the boundary condition. What the effective temperature is well known, the luminosity is well known, and also the, what we call it, what else? Luminosity, temperature, and also the abundance. So the abundance is quite well known for this particular, for sun, for example, right? So when we want to set for one solar mass, for example, we can easily predict how the structure looks like at that particular, what they call it, 4.6 billion years. So it means that the equation, the only will change is for me is the how we choose either radiative or convective. Right? So from here, when we calculate the for the sun, I think at first point it will be purely radiative, and after that it will start to change to convective. I think what is the temperature at certain temperature, but the effect is really small for that particular sun. But if you calculate, for example, for massive star, so for massive star, the key is we don't know what is really effective temperature. We don't know what is the luminosity, and then a lot of variables are unknown. Okay, and then usually we treated our, what we call it, energy transport purely convective, right? So we don't put radiative at all. So we treated only, we choose only 8B, for example. And another thing is because of the stability. Okay, so when we calculate for massive star, this additivity index will play important role. So here, actually, the effect 8A is very small, the effect for the massive star. So the effect will come really great in this 8B. And what happened is if the gamma 2, if I'm not mistaken, we have to comply for the 4/3, the pressure, what we call it, condition. So if the pressure condition is collapsed at certain point, and this equation eventually will lead to your star will die earlier compared to sun. Sun, they have more stability in order for the sun to evolve, for example, at the white dwarf. But for the massive star, the stability equation, what happened is this equation is one of the key points to maintain the stability of star. Another equation for the different mass, okay? So for example, energy here. So energy here for sun, we only consider for nuclear reaction, E, for proton-proton chain or cycle. But if you calculate for massive star, we have to consider another, this E become E nuclear plus E new, neutrino. We have to put another extra term for this one. So the equation slightly changed, but not much, just to ensure that it will fulfill the, what they call it, the output or the characteristic for that particular mass. So that is my answer for that.
Okay, thank you. I got what is that? Oh, sorry. Okay, no question. We still have much time until 9:30 if we follow the schedule.
We stop at 9:30, isn't it?
Yes.
Okay.
9:30, okay.
Okay. So what else I can explain before we what they call it, stop for the what we call it break? Okay. So one thing that I want to show to you, maybe this is I plan to show later on, but never mind. I can show it a bit now. Okay. So this is technically maybe some of you already know MESA. So this is how that we evolve from zero. This is, I think, pre-main sequence. They have pre-main sequence here for this MESA. So they calculate from the pre-main sequence, which is time negative, until the white dwarf, if I'm not mistaken. So these are the parameters that we obtain from our output. We know what is here. We have our mass. That's why we have to calculate the Lagrange coordinate. This is our mass, and then we obtain our temperature, density, and pressure for that particular, what we call it, a star. This is one solar mass. And here, this is the bottom part is what we call as a Kuiper-Hine diagram. So from here, we can see how does our core evolve with times before it's collapse. Okay, meaning that the star eventually will collapse, either it become white dwarf or what they call it, neutron star, whatever. So from here, you can see that the change of how we see that there is an iron, there is silicon, oxygen, carbon, helium, and this is the total. You can see the mass total is 0 until 1. This is for one solar mass, and this is where the time evolve, right? So from here, you can see that for each, what we call it, color here, it will represent what we call as our burning stages. You can see that here the hydrogen is the most dominant, the blue one, and then we have small, I think this is small one, probably the most more heavy element. For example, some hydrogen, helium envelope, and then I think we have some neon and carbon, carbon, core burning, and so on, can be represented for our star. So this is technically the one that already been embedded in the stellar evolution. And from there, we have also the density with temperature. So this is the structure part. So this is where we get the structure. And this one is actually where we get the evolution, the log density, temperature, effective temperature with luminosity. This is what we call as our HI diagram. And this is the log mass fraction when we have our mass evolve. And then we can see that a lot of what we call it, what is this element? I think this is magnesium 24, can be found at the surface of the sun, right? Or what we call it, I think this is white dwarf, no longer sun, because it's evolved quite, what they call it, quite rapidly towards the end. You can see here we have production of oxygen 16 and carbon 12, a lot at the center, but eventually when we go to the surface, everything being decreased, and this is evolved with time. Okay, so when we see that this kind of evolution, you see that a lot of things happening at the same time. So when we want to calculate for star, for example, we have to remember that all equations must be solved simultaneously. When we solve simultaneously, meaning that everything must move with time 0, and then it will solve all four equations simultaneously, and then we get a set of property, and then it moves to another time, it calculates all these 4 equations simultaneously, and then we get the structure. So what happened now is our star technically is kind of like onion. Okay, so for each layer of onion is one structure. Okay, so when you have a layer of onions, they will represent like your time scale, right? So your time scale is moving from particular 0 until surface of the onion, and then after that, each layer do have, for example, if you what they call taste the onion, they have some what they call it, some really some different taste, and when we go to the surface, so this is also can be represented for our star. So when we want to calculate for particular different stellar mass, yeah, so what happened now, this will change. Okay, all this value will change what they call according to different value. So when it's different value, it means that if we have more massive star, okay, so the temperature, density, and also the pressure will become much higher and more denser. Okay, so it depends on what is the metallicity that we cater for our star. So with different metallicity also will affect that is our star what we call it have a certain density that we are desire. Okay, so for example, if we calculate the first star, have you heard what is the first star? Anyone?
What?
First star.
I don't know.
Don't know?
First star.
First star is the star that first star.
Generation.
Yes, the first generation of star. Okay, so first star is the first generation of star. The star that so-called evolved just before the Big Bang. Okay, it formed after the Big Bang. So the all this what they call it the gravitational pull will have and it form a very massive star, which is people say it might be 1,000 or 1 million and so on. And what happened to that particular first star? The first star, the value of metallicity is 0. Z is 0. So what happened now? The initial composition is totally different from our present sun. Our present sun, if I'm not mistaken, our what we call it, our metallicity is 0.02. Okay, so that is 2 values. So for first star, the Z is 0. So when we have Z is 0, it means that the star itself full of hydrogen. Okay, so maybe just few percent of helium, or probably there's no helium at all. It's purely a hydrogen. So what happened? Let me show you the PP chain here. So what happened if we learn in the literature, massive star governed by CNO cycle. Massive star means that the star is greater than 8 solar mass and beyond. It does not start, the burning is not start with the proton-proton chain. It start with the CNO cycle. But for the first star, the nuclear burning will start with the proton-proton chain. So what happened? So it means that the what they call proton-proton chain here is technically, you can see that the years is around 10 power 10, but first star, the lifetime is very short compared to our present sun. I mean, the lifetime probably like 2 or 3 million years only. So what happened now, they have to modify this kind of proton-proton change so that they can estimate what is the lifetime of the first star before it explode and give the what they call it, the ejection to the to the galaxy to form another second generation of star. Okay, so what happened here is when we have to study different type of star, for example, one things that we have to consider is either we are going to study an old star or a new star. Old star do have different composition, what we call it the new star will have a different position. Okay, so I have another question here before I go to explain more. So, right, so there is a question from Daniel Wijaksana, how the equation change if we are trying to model a neutron star or a black hole. Okay, so that is a good question. Right, so when we speak about a neutron star and black hole, what happened is this equation is totally different. Okay, so this is also similar when we want to calculate. Let me see back the equation here. Where is my mass calculation? Okay, this one. All right, so when we see that for the neutron star or the black hole, so from the neutron star and black hole, either we can certain what they call it structure and so on, we still can use it. But what is the difference? The change will be in the pressure. I don't put the equation of the density. I don't put the equation of density here, but the changes will be in the density of the, what we call it, the neutron star. Because why? Another things I forget to mention that we have what we call as the equation of state. Equation of state is the state that depends on pressure and temperature. So when we want to calculate equation of state of the star, okay, so it is very important. So for the star, the equation of state is purely coming from the ideal gas condition. But for the neutron star, we have to use different equation of state. Sometimes, usually people use what we call as a degenerate condition, where we have to consider the quantum mechanic aspect for that, for the neutron, because now our star no longer in a plasma state. Plasma state means that the gas is in the fourth state, it's a fully ionized and so on. Okay, so when we have a neutron star, the element in our star is no longer gas, it's in form a pack of neutron. So where is this neutron come from? The neutron come from the nuclear reaction that it produce neutron here. You can see here. So this neutron here, or this neutron, will eventually form in the neutron star. So there is no longer proton, no longer other element, only neutron. So the equation of state will change in the stellar equation. And there is a totally different way of calculating the, what they call the neutron star itself. If I'm not mistaken, in neutron star, I'm not sure whether it can evolve, but usually people just estimate the structure of the neutron star at one particular point after the, what they call the star finish the burning, and then it form the neutron star. Okay, so here the question for you is the density will change. The equation of density will change. Later on I will add how we calculate the density. And then for the black hole, okay, so here I've done the calculation of black hole before, but this is purely to what we call it, to compare with the one that people observe. So what happened now, when we want to calculate the black hole, we have to get what is when we evolve the star, and then we have to it will stop at one particular time before either before collapse or just slightly is before collapse. We have to estimate what is the mass of the carbon oxygen core. What does it mean? It means that, for example, when we evolve, for example, one massive star, and it will produce the core, the interior of the star is purely carbon or oxygen. No more hydrogen, no more helium, and so on. So what happened now? We have to estimate by using the TOV equation, which is totally different equation, the Tolman-Volkoff equation from the numerical relativity, in order for us to estimate what is the black hole that produced from the evolution. Okay, so before you want to obtain a neutron star or black hole, you have to evolve from what we call, this is the progenitor. Progenitor means that the star produced before it become the final product, either a black hole or supernova or neutron star. So because why? For example, at neutron star, we have to calculate, if I'm not mistaken, the mass is also changed. We have to estimate the Chandrasekhar mass, if I'm not mistaken. Yeah? So from here, the mass is different, the EOS is different. And for the black hole, we don't know what is the mass. We just estimate what is the final mass of the evolution before it collapses. Okay, Vijay, I hope that I answer your question.
Okay.
Is there any from you
Eddie,
or
any other question?
Oh, all right. So my name is Jason Ipra. I would like to ask a question about before that you just explained about the structure of the star. So my question is about how to define the distance from the surface up to the center of that structure, and so how to define how far the the distance of the core and the radiation zones and convection zones. Thank you so much.
you mean that how we want to estimate the time or the radius?
The distance from the surface up to the center, and how to define the radiation zones, convection zones, and etc. Because it's still not quite clear to me.
Okay, so how we want to what they call define either is a radiative zone or convection zone. All right, so when we want to estimate for a star, for example, yeah. So one thing is that these two equation actually, okay, so DTM and these two equation, this is actually for the rate of change of your temperature. So when we want to see that for either our star become radiative or convective zone, it depends on how the what they call it, you can see it depends purely here, the temperature will play the important role. So, and also the pressure, okay. So, and here what I can see that we have what we call as a criterion to choose it. So here I don't put in the slide. So when we have a set this criterion, we have to see that at which particular point we have to see that our star become what we call it radiative, and at what particular time what particular temperature our star become convective. Okay, so here if those two happen, this is what we call as we have what they call it some mixing between radiative and convection. And so when we have a convection, it means that the what they call it, the gas in our star move very fast, rapidly, and this is usually happen in massive star. So the there is some what we call it condition. Let me search what is the condition here. I also don't remember what is the condition we just set in the code. So when we have to see the radiation at particular distance, we don't really what they call it consider any distance for the star. Okay, because why? Here we move with the Lagrangian coordinate. So when we want to estimate what are our radiative or convective, it's just we see that what is at a particular opacity and also the pressure will change, and then the star will change the what we call it convection or radiative with time. So we don't really put certain distance for that, okay, because this is evolution with time. At T0 probably it become radiative, at certain time it become convective when it's a change with the temperature. So I hope that, because I don't really what they call can understand your question just now.
Okay, is it okay?
Siapa ya? Can I? Who's asking just now, in the classroom or in the?
Yeah.
Oh, okay.
Yeah, it actually answered my question. So actually I have another question.
Okay, sure,
may
sure.
I? So I'm actually nowadays doing the research about the stellar evolution using MESA web. So I
Okay.
found that there is a general tools and it is written like detailed profile of the frequency and there is a number, or there's some numbers like every 50 modules to 250 modules. So which one is the best one? Because I find that I just did that research. So I'm using both of them, 250 and 50, but I haven't got any clear conclusion about that. So can you give more information about it?
Okay, so in Mesa, if you see in the Mesa web, there is what we call it, they have option, right? 2, 5, 25, 50, 250, right? So that is what you mean, right? So what does it mean? It means that how many, what we call it, times that it will save for particular models. Okay, so if you see in the Mesa web, if you choose two models, it means that every 2 model it will save the file. Okay, so it means that it will calculate from, I just give a very crude example. So for example, it jumped from T0 until T1, we have 1 file. So they will save this 1 file. So if they say that if they say that file is 25, it means that T0 until T25, it was saved in 1 file. So the detail is not there. So it means that if you choose higher, value of models, it means that it will summarize at a very long time step for 250 models in just 1 file. So that is how they do it in Mesa. I think this is common in any stellar evolution code. So if you choose 2 models, if I'm not mistaken, the time taken for the Mesa to calculate will become longer. So your file will become a lot. So if you choose, this is a bit different. If you from our understanding, we thought that if you have 250 models, it means that we have more file. No, it means that it compressed 250 models in one particular file. So you can test it, you send it, and you observe how much the time that you will receive the file. Okay, so this is also in the in list. If you calculate the Mesa itself in the code, we can determine that how many models that we want to save for our calculation. We can save 50, 10 or something. From my experience, I always save as 10. Because why? Because I make the DT uniform, so that I can observe that the changes from the time from one point to another point, it will be easily we can see the tiny details along the way for evolution more clearly. So from my advice, if you want to test Mesa code, you can test, for example, 25 or 50. I think that will be good enough. It will give you quite significant result for to observe all the changes. So if you take 250, you might not see the structure actually from one particular point to another particular point. So that you can see. Have you tested before? Have you sent? Then you can see the difference between these two.
Yeah, there is one more smooth and the other is not less smooth than the other. So,
okay, but never mind. We will do it this afternoon and see how it will change between these two.
all right, that really answered my question. Thank you so much.
Okay.
Okay. There is another on the YouTube, but still the same person. Will the magnetic fields around the Newton star be a factor in the model? Regarding his question about Newton star.
Again, Newton star, right? So about the magnetic field. Okay, so technically, historically, most of the calculation in the stellar models, they don't include magnetic field. And there is a popular question is people say that, where is this magnetic field come from? Okay, so one thing is that in Newton star, well, technically the magnetic field usually is quite a new, emphasized in either calculating a Newton star or in a star, because when we want to calculate magnetic field, it usually coming from the angular momentum. Okay, so when we speak about the angular momentum, it means that the star must rotate. Okay, so the rotation is usually not be implemented thoroughly in a star compared to a different, way of thinking, because usually people even in sun we consider when we calculate is a static static star. We don't include the rotation, although there is a very small rotation. So in order for us to include the magnetic fields, we have to consider the rotation first, and then when we the rotation, and then we have to see that how the field of the angular momentum will affect the neutron star. So the answer of the question is you have to include more parameter before we consider the magnetic field. So the magnetic field also can come from the movement of the neutron itself that vibrate inside the neutron star, but that is totally you need to know what is the quantum mechanics behind what we call neutron star in order for you to understand that, which is I don't touch in this lecture.
Okay, thank you. Didn't know. Okay.
Anything else?
Anything else? Okay, Dr. Lisa, maybe one for me, but only to emphasize about the question from Hiskia.
Okay.
About the radiative and convection zone, maybe can we explain it from the Kippenhahn diagram that you saw?
This one.
Yeah, from the movie, from the MESA.
Hold on. Yeah, this one, right?
Can we see from that panel on the middle about the convection, the change of the convection, the radiative convection?
Yeah, this one, right?
Yeah, solar, okay.
I think this is one solar mass. Yeah, so we can see it here. Convection zone, right?
Yeah, one solar maybe.
Yeah, this is for one solar mass. Let me see. Convection zone.
The change of the radiative and convective zone, maybe.
Hold on. Okay, so the convection zone is actually at the outer layer. Let me see, it's still moving. Can we stop it at a certain point? I'm trying to make it not moving. Okay, so when we see this convective zone is actually at the outmost layer, right? So here, do we have the convective zone here? Let me see. So convective zone usually at this, what they call it, at the surface. So let me see that it will move.
One solar.
Yeah, it's well, the surface is around 0.5 or something like that, up to the value. So here we have what we call it a very slight convective zone, which is around 0.5, what they call it, solar mass up above here. I think this is hydrogen, if I'm not mistaken. Let me have to see what is the parameter for this one. And here is, but this one is actually, I think, already moved to the white dwarf condition.
Yes.
This is no longer sun, if I'm not mistaken. And then the convection, okay, so convection is here around, the density is around 0. I don't know what is the value here, cannot see it clearly. So you can see that also in the density and model number, you can see that here there is a convective zone happen at this particular point. When it reach, this is what happened is because the density is already changed with what we call it with time here, because it's already reached the white dwarf, and eventually the radiative zone is changed to, accordingly to the convective zone at this particular, if you can see it clearly here. So the distance is around 0.5 solar mass here.
Okay. Okay. So
yeah, the radiative zone is, I hope that I answer the question correctly.
Okay. Okay. Maybe another one from the chat. does the equation we discussed could predict trigger for supernova as well?
Yes.
Okay.
The answer is yes. Okay.
Yes.
All right. So the question that predict trigger for supernova. Okay. So for supernova, usually what people do is they know what is the light curve, right? So the light curve for the supernova, and also the what we call it. So the I think the abundances. For example, that nickel 56, for example, the abundance that produced from the supernova. So what happened usually, okay, so this is similar attempt when you want to calculate the black hole, but only the black hole we have to implement the Tolman TOV, Tolman-Oppenheimer-Volkoff equation. But for the supernova, we don't do that. Okay, so for supernova, what we do is we have to use input from the stellar evolution code. For example, you can take at the silicon burning stage. We evolve until silicon burning stage. This is for massive star. And then we have to take that structure, and then we have to do a hydrodynamic test. Okay, hydrodynamic test means that we have to put in different models. Okay, so stellar evolution code cannot explode supernova. Okay, so we have to do a few things. That this is what I've learned from other people's too. First, you have to do some nucleosynthesis mapping from our stellar evolution. Okay, so for evolution, we have abundance everything, so we have to do some nucleosynthesis mapping. And after that, this mapping is, we have to use it as an input for a supernova models, which is what we call as a hydrodynamic. The one that we use stellar equation is hydrostatic models. Okay, so hydrostatic and hydrodynamic models is two different things. Okay, because the equation of state is also different, the density and temperature is also different. And then we choose that for the, what we call it, this structure of our star here that we calculate here, we have to input and the hydrodynamic models, and then we have to put different energy in the models so that it will explode as supernova, and then it will reproduce the light curve. So if the light curve from hydrodynamic models is not similar that observed, we have to redo the stellar evolution. Maybe we change the input physics, whatever, and then we have to recalculate it, but do the mapping again and recalculate back again. So that is how people do the supernova calculation.
Okay, thank you. Maybe we have stopped for the break for 15 minutes.
All right.
Lisa, thank you for your presentation this morning.
Yeah, thank you.
Okay, we'll take a break until 9:45.
9:45. All right.
Okay.
Thank you,
Okay.
Abila.
Okay, thank you.